So our second speaker in today's double header is S. Ramakrishnan. So Ramakrishnan is soon to be doctor. He's going to have his PhD defense at IIT Madras on
Next week.
24th.
Oh, 24th.
24th.
How can you do that?
And
Christmas.
So let's in advance congratulate him for going to become a doctor. So he's been therefore a pre-doc here for about a year. Since about last December, he has spent time with us. So today he's going to speak about completely uncoupled algorithms for network utility maximization.
So this is a part of my PhD work. So I'm glad that Alex is here. So I'll get enough questions and training for my defense.
And Rajesh also.
Ask questions. So this was done in collaboration with my guide, Dr. Venkatesh Ramanan from IIT Madras. So I'll start with an example to motivate the problem. Then I'll describe the system model and talk about the related literature. And I'll propose two algorithms which are completely uncoupled and which maximizes the network utility. And so why do you need to do a completely uncoupled algorithm? It's distributed resource allocation is always better in the sense that it is robust and it avoids unnecessary overheads. And also in applications like channel selection, user association, power control, you would like to have a fair solution. Like each node in the network would like to get a fair share of the network throughput or something like that. And also, like central control is not viable in a heterogeneous network where there are access points with multiple operators and so on. So there is a need for completely uncoupled algorithms. What I mean by completely uncoupled is lacking of the actions or the payoffs of the other nodes in the network. So I'll start with a simple example, user association example. There are two users, user 1 and 2, and there are two access points A2 and A1. So each of these users can associate to one of these access points, and depending on what the associations are, they get a payoff. So for example, let's say user 1 gets associated to A2 and user 2 gets associated with A1. Then user 1 gets a payoff of 1 and user 2 gets a very small payoff. And on the other hand, let's say user 2 gets associated to A2 and user 1 gets associated to A1. In this case, again, user 2 gets a good payoff and user 1 gets a very small payoff. So if in the other case, and in the other two cases where both the users gets associated to the same access point, they both get a very bad payoff. This is the example, it's just a cooked up example. So in this case, if you would like to maximize the sum payoff, you'll always choose A2, user 1 will choose access point A2 and user 2 will choose access point A1. And that is unfair to node 2. And so an ideal situation would be to time share between the action profiles A2, A1 and A1, A2. So that is what we'd like to do, and we'd like to do this in a completely uncoupled manner. So this is the rate region for that example, and this is the sum rate maximization point, and this is the Nash equilibria, and you can see that both these are equally bad, and we'd like to operate somewhere here so that the system utility is maximized.
They're equally bad.
Not equally bad. Okay, this is good for one of them, and this is bad for both.
And where you would like to operate?
Like to operate somewhere here so that it's fair to both the players, and you give a good amount of network throughput also.
Can you describe what fair is?
Fairness for me is utility maximization. So I'll just get to that.
Oh, the sum, huh? You don't put any weight or anyway, you just take the sum.
Yeah, sum of.
Okay.
I'll just.
You will define it?
Yeah.
Okay.
So this is the network model. There are M access points and N users. So at each time a user gets associated to an access point, and depending on the associations, each user gets a payoff. So the set of, let's say user 1 can get associated to a set of access points A1, user 2 can similarly get associated to a set of access points A2 and so on till AM. And let's say at time t, user 1 gets associated to A1, user 2 gets associated to A2 and so on till AM. Then each of these guys will get a payoff R1 of t, which is a deterministic function of all the actions. So we assume that Fi's are deterministic. And similarly, user 2 gets a payoff, which is a function of the joint action profile, and so on. And we also assume that this Ri is bounded and it's strictly bounded by a number which is less than 1. So to summarize, there are m users and n access points, and time is slotted, and every time slot, user m associates with an access point am, and depending on the association vector, each node gets a payoff. And we assume that the payoff is bounded by some alpha which is less than 1. So our objective here is to maximize the sum utility, where this utility is a function of the average payoff, where Rm bar is the average payoff, and like this average payoff could be got by time sharing between different action profiles. So yeah, we'd like to maximize this sum utility, and this is fairness for me. Like so. Yeah.
Yeah, I don't understand why you talk about the time before. You define A of t, and now you define something without t.
No, so yeah, okay. A is an action profile, and P of A is a fraction of time I choose action profile A.
Okay.
So if I choose P of A fraction of time action A, then this is the average reward that I get.
No, so can you explain a bit more? So P of A is the fraction.
So there are a finite set of action profiles.
Okay.
And you can time share between them.
Yes.
So depending on the like for each action profile, you get a payoff. And if you time share between two of them, you get an average payoff.
And what is F or FM is the delay
FMA is the payoff that you get for action profile A.
at M. What is
M?
M?
Is the node.
M is the node. Oh, you just do the average, okay.
Yeah.
Then why you take UM of the average and you not just write summation of the PA UM of FMA?
Yeah, I'll get to that. Like it's you can take the Lagrangian and do something. Like I'll get to why I'm doing like this. Why am I writing like this?
Okay, that you put the average in the utility and you not compute the average utility.
Yeah. No, I didn't get your.
So his question is that why is utility function of average rate and not
Thank you.
actual payoff which you get? UM of FM of A.
So okay. So let's get back to this example. Like, let's see, like if it's 1 and you take log of 1 or something, some function of 1, it can still be the case that this is bigger than this number. So you might still be unfair.
No, so suppose I get half the time 1, half the time I get 0.05. So on average, maybe I'm getting.
Why are you not averaging the utilities is the question.
Thank you.
No, like so even.
No, I don't understand the meaning of this quantity. I don't understand what you are trying to maximize. I don't understand what is the meaning of this.
This is the standard way in which it's done, because your rates accumulate and it's your average rate that you get, long-term average rate.
Okay.
The utility is on the long-term average.
Okay. It's like it's already stationary, so
Yes.
okay. I guess I understand. Did you remember what he said, or did you understand, or not?
Yeah.
Okay.
So this problem might not always be solvable, like in a completely uncoupled way. So we need to put more assumptions on the network, and the popular assumptions that are there in the literature.
About the actions,
Yeah.
they're supposed to be the same for all players. Is there a subscript M?
No,
there?
this A is a vector. Like, I'm sorry for the bad notation.
I see. It's just like some scenarios.
No, A is like, so let's say you pick an action A1 and I pick an action A2. A is A1, A2.
But A is a vector is given there, so it's not bad notation.
Oh yeah,
Good notation.
It's a good.
It's notation.
So yeah, like this problem cannot. Yeah, your question. This problem cannot always be solved in a distributed manner because of the dependence. So you have to put some more assumptions on the network, and the popular assumptions in literature are interdependence and graph-based models. So in graph-based models, they assume that your payoff depends only on your neighbors, and like with CSMA and stuff like that, you can get an estimate of what their actions are, and so you can make it distributed. And interdependence is another assumption. Like, so let's say you divide the set of players into two, S and S complement, and you fix an action profile A, and AS is the action profile of the players and like the users in set S, and A minus S is the action profile of the users in set minus like S complement. Now for any such division and any such action profile, there exists a J which is not an S, and an action profile change in S that leads to a change in payoff. So when you don't change your action and you see a change in payoff, it means that somebody else in the network has changed their action. So that is a way of learning that somebody else has changed in their action, and this is what we'll exploit to maximize the network utility in a completely distributed way.
And what is your notion of neighbors?
No, there are no neighbors here. Like
No,
the
on this
graph-based
one.
models, you assume wireless network and
No. So if I go back to your optimization problem,
No,
just
it
before.
doesn't come in
Okay.
my model. Like, it's a different model.
Okay.
This has been like very well studied, and I don't think they've studied this assumption as much as the CSMA.
No, I'm just saying that you give an assumption which is not related, but we cannot understand in your setting what does it mean. That's it.
No, it is very popular in like QCSMA, all those algorithms. So like I just mentioned it so that
Okay.
people who know can relate to it.
I don't know,
No,
so I cannot
it
relate.
is kind of-
It's okay.
So on the interdependence assumption, Aradalski and Young came up with a strategy which, like among the set of Nash equilibrias, it maximizes the sum rate. And Marden proposed an algorithm which achieves sum rate maximization. And Marden also proposed an algorithm in 2015 which achieves among the set of correlated equilibria, it maximizes the sum payoff. So these papers achieve only a few points in the rate region, and we'd like to maximize the network utility. And in the conflict graph setting or the graphical model, there are a lot of papers, starting with Jiang and Waldron in 2010, who proposed an optimal algorithm for concave network utility maximization problem. So I'll stick with this interdependence assumption, and I'd like to do basically what Jiang and Waldron did in this assumption under this setting. So my objective is to ensure fairness by time sharing, and for me fairness is maximizing the sum utility over the average payoffs. So we'll propose two algorithms, one for concave utilities and one for general utilities. I think I mixed up this. Sorry for that. And utility maximization ensures fairness. And this interdependence assumption, if you generate the payoffs randomly and assume that both two payoffs cannot be equal, then like any game satisfies interdependence. So it's what I'm trying to tell is that there are a large class of games with this assumption.
Sorry.
So if if I just generate payoffs at random, like for let's say there are two players, and you have to choose payoffs between 0 and alpha.
Can you put the definition there though? Interdependence. Yeah, while you explain.
Yeah. So let's say if the payoffs are different for each action profile, then it satisfies interdependence like trivially. So and
Say again
that is
what
a
you
large
just
class
said.
of games. Is what.
Say again what you just said.
So if for each action profile,
Ah.
the payoff is different.
Yes.
Like
Yes.
For every action profile, like
Okay. You don't have symmetric actions. You don't have okay.
Yeah, you don't
a symmetric
have,
payoff.
Yeah, and then interdependence is satisfied. That's what that statement actually means.
Is it defined only if that?
No, it does not define only if. Like, so if suppose for every action there is a like any two action profiles there is a difference in payoff, then it satisfies interdependence. Interdependence just means this. So let's say I divide the set of players into two, S and S complement, then and I fix an action. For any such separation and an action profile, there exists some action profile change in S that can cause a change in payoff in some user in S complement.
You just need.
So
one
let's say
set.
we are all playing a game, and I divide you in one, I put you in one set, and everybody else is in another set. So let's say the states are like everybody is listening and you're doing something else. Let's say you're talking or something like that. So if you change your state to listening, then it will change the reward of somebody else in the network.
In the other set.
In the other set, yeah.
And it should be valid for every set subset.
Every such division and every such action profile. Like others don't change their action, like you are changing the action.
So in the example, previous example,
Huh.
the payoffs were same for both the users.
This one.
Yeah. If it was 1.001 and similarly for A2.
But then, like, in the
That
sense,
doesn't satisfy.
see, these payoffs are all different, right? Like, for each user, the payoff is different.
So if it was instead of 0.8, if it was 1.
If 0.8 instead of 0.8, if it was 1, then
Doesn't satisfy.
yeah, it doesn't satisfy. Yeah, so I'll present the first algorithm, which is for concave utilities. And so recall the optimization problem, which is maximizing the sum utility over the average payoffs. And like the assumption here is UI is increasing strictly concave and UI dash of 0 is less than V. So like convex optimization tells you that you can take the Lagrangian and put this term there, and so that's what you're doing. Like so, you take the Lagrangian for this constraint. So you'll get a UI of Ri bar minus summation over I, the Lagrange multiplier lambda I times Ri bar minus summation over AP of Ri of E. So this can be split into like two problems, like UI of Ri bar minus lambda I times Ri bar, and another term which is sum over P of A, and I've just interchanged these summations, and it's sum over I lambda I times Ri of A. So any questions? So here, like I'd like to maximize, like you to get the dual problem, you'll like to maximize it over the primal variables, which is R bar and P. So like this actually naturally splits into a problem over R bar and a problem over P.
So I think you miss a couple of steps, right? Lambda I should be positive.
Yeah, lambda I should be positive.
And what else I wanted to say? I think that's it for now. I was thinking of something. Okay, yeah, you had to add that lambda I is positive.
So like why did I do this? So if you see this equation, it is actually like coming out of the summation. So this can be optimized in a distributed way. Like see, like the summation can be taken inside, and each user can independently solve this.
And also be careful because you switch. I've seen that you switch from equality to inequality, which is okay because it's just that the constraint has saturate. But
Yeah, it's because
Yeah,
you're
yeah.
maximizing
I know,
all
but
utilities and which are increasing.
yeah, but you switch. You have switched for this constraint, and you have also switched for the rate constraints, and you didn't say it for
Yeah.
this one.
Yeah.
No, just
Yeah.
you have to tell at some point, right?
So yeah, so this problem can be solved in a distributed way, and this is the difficult thing. So the maximization is split into two parts. where a maximization over R bar, and this problem can be solved in a distributed fashion, and the maximization over P, and this is like you have a weight for each action, which is summation over I lambda I times Ri of A, and we'd like to maximize this, like choose the action which maximizes this weight.
Can you go back just to the previous slides?
This one?
Yeah.
Yeah, so you have a term, this one, right? Like this
Okay.
is the same.
Yeah. Okay.
So for this, we'll use the approach that was used for solving this problem, we'll use the approach that was used by Marden and Young, who like solved the sum rate maximization problem. Like if you see this problem, this is just maximizing the sum rate with weighted rate, kind of like weights with weights lambda I. Right? So I'll now focus on how to solve this problem, and notice that this problem is like easy to solve. So like for each node M, I give a satisfaction variable, which is a binary variable qm of t, which is 0 or 1, which can take values 0 and 1, and qm of t is 0 when like the node is unhappy with the current action and payoff, and it's 1 when node M is happy or content with the current payoff. And each node has a weight lambda M, and at time t, user M has to update its action and its satisfaction variable qm of t. So like I'll tell you how it updates its action and its satisfaction variable. Like any questions so far? So suppose user M was content in the previous time slot, then it chooses an action which it shows in the previous time slot with a large probability, 1 minus epsilon power c. Here epsilon is a small number, and it chooses any other action at random with probability epsilon power c. And whenever user is M is discontent, it chooses an action uniformly at random. And now we have chosen the actions, we have to update the satisfaction variables. So suppose if user M was content in the previous time slot, and it shows the same action that it shows in the previous time slot, like AM of t is equal to AM of t minus 1, which happens with a very large probability, like 1 minus epsilon power c. And also your payoff doesn't change, then you become content or happy with probability 1. In any other case, you become content with probability epsilon power 1 minus lambda M times Rm with a normalization. Like this normalization is used so that this is a probability term. It's less than 1 to make it less than 1. And
Define content.
it's just a 0-1 variable, and like how like it's a variable that is used to coordinate amongst people. So like
Is it the rate update by the user?
no, it is not. So in some sense, if you see this thing, you become like when you're discontent, you become content with a probability epsilon power 1 minus lambda M times R.
Oh, it's plus 1. Okay.
So
Zeros, one.
for every user to become content, it will be like product of these, and that will turn into epsilon power n minus sum over lambda M times R. So you'll like try to maximize the sum lambda M R.
So QM of t, I understand it's an auxiliary variable which came while you're solving the dual. But what we're asking for, what is that equation which the QMT evolves itself? No?
Yeah, this is the evolution. Okay, this is the evolution. So if suppose qm of t minus 1 was content, and you choose the same action that you chose in the previous slot, then you become content like that qm of t is 1 with probability 1. And in any other case, qm of t is 1 with probability epsilon power 1 minus lambda M times R. And you become like it's 0 with probability 1 minus epsilon.
So the probability is evolving for the indicator.
Yeah, the probability is
So it's like a two-state Markov chain with
like,
inhomogeneous
For
transition.
now, assume that lambda M is fixed. Like I'll get to that case where lambda changes. So like this actually this algorithm induces a Markov chain over the state space A, 0, 1, M with a positive stationary distribution pi epsilon. Like you can show that it is irreducible aperiodic and all. So it has a stationary distribution. And so like we are interested in finding out the performance of the algorithm as this parameter epsilon goes to 0. So
Lambda is fixed.
Yeah, lambda is fixed.
yeah.
In the lemma.
Yeah, lambda
In the
is
lemma.
fixed.
In the lemma, lambda is fixed. Yeah.
And perhaps you should also say for fixed lambda.
Yeah. So I'm interested in like looking at the performance of the algorithm. So the performance of this algorithm can be obtained by its stationary distribution in like its long-term performance, and I'm interested in the stationary distribution as epsilon goes to 0. And I call the set of states which has a positive probability when positive stationary probability as epsilon goes to 0 as the set of stochastically stable states. So like I'm interested in what happens when epsilon becomes 0 in this equation. So let's try putting epsilon equal to 0 for now. So let's say if epsilon equals to 0 and I am content in the previous slot, so then I pick the same action that I chose in the previous slot. Suppose if I were discontent, I anyway choose an action at random. And if I were content in the previous slot, I'll always choose the action that I chose in the previous slot. And if I see a change in payoff, then I'll become discontent. Like so, when I put epsilon equals to 0 here, I become discontent with probability 1, and if I put epsilon equals to 0, I become content with probability 0, like in this case. So to summarize, like see, when I'm content, I've put epsilon to be 0, and here aim of t is chosen to be aim of t minus 1 with probability 1, and whenever I'm discontent, I choose an action uniformly at random. And how do I update the satisfaction variable? Again, I have already chosen the same action, so this constraint doesn't matter. And if my payoff is the same, then I continue to remain content. And if the payoff is different or in any other case, I'll become discontent with probability 1. So let's say if every user in the network is content, then they'll all choose the same action that they chose in the previous slot. And they won't see a change in the payoff because they are choosing the same action.
So 1 second, I just realized something. T right now is T capture the update of this algorithm.
Yeah.
And this is the same T for lambda.
No, I'll get to lambda later. Like
But you
lambda
already-
is fixed for now.
Okay.
Let's say lambda of t is lambda.
Okay.
So if everybody chooses the same action, then everybody will continue to and everybody were content. Everybody will continue to remain content with probability 1, and the process continues like that. Suppose if one of the let's case the other extreme case where everybody is discontent, then they'll all choose an action at random, and they'll continue to be discontent because and this is what it happens. So whenever everybody is discontent, they'll be choosing actions at random with probability 1. So if one of the nodes is discontent, and then by this is where interdependence assumption comes in. So if one of the node is discontent, it chooses an action at random. So this induces a positive probability of seeing a change in the payoff for some other node in that. So this makes sure that some other node in the network becomes discontent with probability 1. This is all this analysis is when epsilon equals to 0. So eventually what will happen is if some node is discontent, eventually all the nodes in the network becomes discontent with probability 1.
It's not clear.
So okay, let me. I'm saying that at least one of the node is discontent in this thing. So if I'm discontent, then I'll choose an action at random, right? By the interdependence assumption, let's say I'm one set and everybody else is in the other set. So then somebody else in the network will see a change in payoff. So if they see a change in payoff, then they become discontent with probability 1. So by extending this argument, everybody will become discontent with probability. So if you think in terms of Markov chain theory, there are like multiple recurrent classes in this Markov chain when epsilon equals to 0, and the objective is to figure out which Markov chain will have a positive stationary distribution as epsilon goes to 0. So I'll describe a simple Markov chain and to show what it will be. So let me consider a two-state Markov chain. So like this can be, like the stationary distribution of this can be calculated easily. If you have to guess based on just looking at this, what will be the stationary distribution at this, like for state 0 and state 1 when epsilon goes to 0, like can you guess? Let's say, so from state 0 to state 1, it transits with probability epsilon. And from state 1 to state 0, it transits with probability epsilon square. And I'm asking the question, what will be the stationary distribution as epsilon goes to 0?
1.
1 for?
State 1.
Yeah, state 1. Yeah. It'll go to state 1. So if I consider, like let's say a three state example. So if I consider a three-state example like this, so from state 3, all the outgoing nodes go with probability epsilon cube. There is self loop as well. From state 1 to state 2 and 3, it jumps with probability epsilon, and from state 2, it jumps with probability epsilon square. In this case, where will it go to?
There's one epsilon cube. So yeah.
So it will go to 3.
Yeah.
So let's say if I just change it like this, like epsilon square here, then it's like a little bit tricky. And so what you can actually do is, like, what I'm trying to say is, it all depends on the rates at which these epsilon goes to 0. What will be the stationary distributions? So there's a theory which states that, like, if I construct a graph based on this Markov chain, and so I'll consider all trees like with a particular node J, and I calculate the rates at which it goes to 0. So for the other example, it was epsilon and epsilon, right? So the rate is like 1 and 1 here. So I'll consider all trees for each of these states, and I'll calculate.
By rate, you mean the power of epsilon?
Yeah, the power of epsilon. Rate at which it goes to 0. So I'll calculate for each node. I'll calculate the power of epsilon, and I'll sum over the rates over these edges. And for each such node, I'll take the minimum such tree, the tree which minimizes this rate, and if suppose, like, so I'll call that minimum as Rj. This is the rate of a tree which is rooted at J, that is like a tree where all the incoming nodes come and settle at J, and like it's the sum of the rates of the edges, and I take the minimum of that over all trees. So like the theorem is like the stochastically stable states will be the states which have the minimum of these rates. I think that not a bit.
Can you write down the R of J?
So let's say for this node, like node 3, this is one possible tree. So for this tree, R of this tree, the sum of rates is 2 plus 1, 3. And there could be other possible trees. Let's say this is another tree, which is still rooted at 3, right? And this could, so this is again, for this example, this is again 3. And I find all such trees and I take the minimum of these rates. And that minimum I call as R of G. Right? So what I'm saying is like, so a state will have a positive stationary distribution if this R of J over all J is minimum.
Okay.
So, so this is, so like in our case, I told you that there are only like 2 sets of recurrent classes, one where everybody is content and one where everybody else is discontent. So let's say everybody is discontent. In that case, for everybody to become content, they have to go through this. So everybody is discontent happens with like you choose an action with a probability that's independent of epsilon, and then for you to become content, you have to become content with the probability epsilon power 1 minus lambda mrm. So for all these nodes to become content, it will be like product over epsilon power 1 minus lambda mrm. And so this, because it's a product over exponential, it becomes a sum in the exponent. So the rate at which it jumps from a discontent state to a content state is n minus lambda m times rm. So I am trying to minimize over n times lambda m rm. So that would mean maximizing over lambda m rm. This is the like kind of idea of the proof. So yeah, so the theorem is the stochastically stable states of the Markov chain is the action profile that maximizes lambda m times rm of A. So now we know how to solve this problem. In this problem, we already know how to solve this.
Okay. Can you go back to the problems that you were trying to decentralize? So I think
Yes,
the slide
this is the problem that I'm trying to decentralize.
in PA.
Yeah, in PA.
Okay.
And the algorithm that I told you will solve this problem. And this can be solved like easily.
I is a user, right?
So, but we are not done yet because this only solves the primal problem, and we'd like to we should optimize over the dual as well, like over these lambdas as well. So, so the
1 second. Okay, not that. Okay, thank you.
so now like consider what like. I wanted to understand what this lambda is actually doing in this equation. So let's say there is no lambda I Ri bar here. So there is only summation over I ui of Ri bar. Then each node will pick the maximum possible Ri bar, that is alpha, right? So in some sense, lambda I is putting a cost on this, on the choice of Ri bar that you can make. And so if suppose, and this is actually the realized average payoff. Array bar is just an auxiliary variable. So if suppose array bar was bigger than P of A times like the payoff that is achieved, then you will tend to increase lambda I.
There is something that I don't understand. When you try to optimize P of the second part of this the second part, right?
Yeah.
The only thing is you are looking for the maximum or the K maximum value of a summation of I lambda I R I of A,
Yes.
right?
Yes.
So why you just establish a communication where everyone is just sharing their own value?
Yeah,
You
but
just do a
I'm
scheme where
interested
I'm
in.
asking you, so here's my value, you register it, you compare with yours. If mine is bigger than yours, you put it,
Yeah.
and then you
can
transmit.
do that. So what happens by doing that is the complexity of your you're actually going to run a gradient algorithm on top of this, and when you do that, like at each gradient step, your complexity will be like exponential. In
No, it's not exponential, right? Because
it's
the
a
only thing
combinatorial optimization.
you just need to find a path in all the graph. The only thing to compare all the value
yeah,
is just to find.
even
So you
if
define a
know-
path.
Even if you know all the values,
Mm.
let's say even if you know all the values,
Okay,
the complexity is exponential, like because it's a combinatorial optimization problem.
it's not. Assuming that between all of us, I define a path of communication, one path.
Assume that you know.
I'm
all-
giving to you.
You know the payoffs. Assume that you know the
Combinatorial
payoffs.
optimization is in the set of choices A. So the
Oh.
path length can be exponential in the number of users.
Oh, okay.
And also the framework in which he is operating is the only communication you have is through the R, nothing else. You take an action, you observe. You take an action AI, you don't even see what others' actions are, you only see the RI of A,
Oh, okay.
which is the realized
Okay, so you don't communicate.
action. No communication possible other than observation of the RI of A.
Okay. Okay.
Yeah, thank you. So, if you see what lambda I does, it puts a cost on you choosing a very large enough Ri. So, suppose if Ri bar is bigger than this average payoff, then you will tend to increase lambda I and say that you'll have to decrease your Ri bar. And suppose if Ri bar was less than this average payoff, then you'll try to reduce your lambda I. So, yeah.
Sorry, for the second optimization, right? It's just a linear optimization.
Yes.
So wouldn't PA be put full mass on one?
Yes, it will put full mass on one of those.
Or
Which one?
perhaps.
The one which maximizes some more I lambda I times RA of A.
There are exponentially many.
Exactly.
So the dual of this problem is minimizing over. So the dual of the problem is minimize over lambda, d of lambda, where d of lambda is maximum over R and P, the Lagrangian. So it also turns out that whatever I told, right, like RA bar and this, it actually turns out that summation over AP of RA of A minus RA bar, where RA bar and P are the primal optimal solution, is the subgradient for the dual problem.
So a comment just to address Nitin's question. So even here, he's actually going to take a long time to converge. But the point is that you can take only AI, he can take only AJ. So whereas when you want to find out where the optimum lies, that's an R of A, it's a joint action. How do you get to that? So the problem is not one of, it is exponential, and his search time is going to be, the convergence time is also going to be extremely large. But the point is one of non-coordination. The coordination is only through the observed RIs.
And also at each time your complexity will be order of 1 or something at each time step. So let's say you have to choose your action.
Can you, perhaps you will have done later, but can you define exactly the metric in some sense that you are trying to minimize in terms of what is the of
No, okay. In terms of that and all, assume that there is no coordination, you cannot talk to anybody else. And how do you
I'm
maximize?
asking what is the scenario in terms of power of each unit? Means that why it's more important in your case that you do only one operation at each time at each node, that you can do multiple.
So for instance, consider the scheduling example. For let's say there are a large number of nodes, you cannot choose an action every time step based on a max weight algorithm, because it will be its complexity will be large. So you'd like to choose an action at each time with a small complexity and try to assume that you can converge.
So it's not really, I didn't formulate well my question. When you study decentralized algorithm,
centralized algorithm.
No, decentralized. I'm pretty sure there exists some metric saying why we want to go to decentralized compared to another one.
Why we want to go to decentralized?
This decentralized algorithm compared to another one.
This is the sort of minimal interact. The only thing that you get to see is the reward. RI of A is all you get to see, nothing else.
No, but I do agree with that, Rajesh. But the question, he proposed an algorithm, but how can I evaluate that it's better than another decentralized algorithm? Perhaps the cell
No,
at
for
different
this-
power, perhaps we don't care about convergence, because if
So he's
convergence
addressing
is
a
not,
conceptual question. Is it possible at all? Does there exist an algorithm at all which will get me to the network utility maximizing action?
I do agree, but I'm pretty sure someone of his defense will ask also this question about, okay, you have addressed this existence.
No, I think you are.
Okay.
You ask. Don't worry about his
Okay.
defense. He'll handle that.
No, but I think it's an interesting question, and also how to evaluate this algorithm in a general setup, right? Can we, we have regret for centralized algorithm and so on. Is there something?
No, like for this setup and for this objective, there is no decentralized algorithm which can maximize with the assumptions that.
Because we can think of perhaps 2-3 different algorithms, and how can I compare
No, see,
them?
this your payoff can depend on the actions of anybody else.
Yeah.
So it is like it's very very difficult to optimize a network utility when you have
No,
such.
but for example, this scheme, this Markov chain scheme, I can think of other way.
You can think of other way of
Other way
implementing
of
this.
converging to this optimal PA.
Just a quick time check.
Okay.
You also have the completely general
Okay,
utility
so I
functions,
stopped.
and you have only about 10 minutes.
So I stopped asking questions.
So yeah, I update lambda m by this way. This is the subgradient descent, and this is your this is the negative of the subgradient, and so what I like there are so now here Sm of j is given by a Markov chain, so Sm of j is not a constant. So there are two ways of approaching this. So one is stochastic approximation and saying that this Markov chain runs at a faster time scale as compared to the gradient algorithm, and say that hopefully it will converge. And then the other thing is you run the Markov chain over a frame of a frame which is long enough so that the Markov chain converges. I'll use the second approach where I'd like to estimate what the size of this large enough frame is. So I'd like to find out the mixing time of this Markov chain. So the mixing time of this of a Markov chain is defined as, let's say, pi e epsilon be the stationary distribution of Markov chain x epsilon, and pi tx be the distribution at time t with initial state x. And then the mixing time is given by, if you consider the variational distance of pi t x, that is the distribution at time t with initial state x and the stationary distribution, it should be small enough. The variational distance should be small enough, and overall initial conditions x, and you try to find the minimum t which can attain this. And this is the mixing time. This is the definition for mixing time of a Markov chain. And for we show that the mixing time of this Markov chain is bounded by epsilon power c plus 1 times n, 1 by epsilon power c plus 1 times n. So it's the mixing time is exponential in the number of nodes. And to show this, we use Dobrushin's ergodic coefficient and its inequality. I'll skip the details due to lack of time.
So here the epsilon is held constant.
Yeah, here the epsilon is held constant.
And the zeta is, you will come to the
Zeta
zeta
is-
through the various trajectories, and you will take a minimum across all possible.
No, zeta is how close I should go to the
I see.
station.
That's just the mixing tempo.
Yeah.
And what you call a threshold for mixing. Okay.
So, for a fixed frame size, which is n times, v here is the, if you recall the assumptions, I told that ui dash of 0 is less than v. That is the v here. and divided by, I'll state what the zeta is, times epsilon power c plus 1 times n. This comes from the mixing time. And for decreasing step size, we show that the utility over the weighted rates, where the rates are weighted by the step sizes. And this is bigger than the maximum utility times a term which is like this term comes from the fact that the Markov chain is like the epsilon is fixed in the Markov chain. So this is the error term that comes from the fixed epsilon in the Markov chain, and the zeta comes from the mixing term. So this is the total error in your utility. And this array bar is still not the achieved payoff, so you have to show that this array bar is equal to SI bar, and that also we show. And for fixed step size, B of t equals to B. Like you have average, like utility over your average payoffs instead of the weighted average. And in the error term, you have an additional error term which is coming due to the fixed step size. And here also there is an error term because like array bar will not be equal to SA bar, but it will be bounded by some B plus 1 by B. And for yeah, so and R star is the solution to the optimization. And yeah.
Where exactly do you use single dependence?
In the Markov chain, I told you that the stationary distribution converges to the max weight rate. There, only there I used. So the other algorithm is fairly simple. Like so, I kind of discretize the rate region. I'll just explain. Like, so each node has a internal satisfaction variable Qm of t, and like I keep track of the last k actions and last k payoffs that I received. So this k is some kind of like I discretize the rate region. Like you'll understand once I show the algorithm. So at each time user M has to update its action and its payoff. So I choose the, like if suppose I were content in the previous slot, I choose the action that I chose k slots before with a large probability, and with a probability epsilon power c, I choose an action uniformly at random. And again, when I'm discontent, I choose an action uniformly at random. So when I'm content, and like this is for the action profile, action update, and for the satisfaction update, suppose if I were content in the previous slot, and if I chose the action that I chose k slots before, and I received the payoff that I received k slots before, then I remain content with probability 1. And in any other case, I'll become content with probability epsilon times 1 minus the utility, where the utility is a function of the average rate taken over the last k rewards, and 1 minus of that is you become discontent. So like so this algorithm is you're kind of discretizing the rate region, and for a large enough k you can go closer to the rate region, but then the mixing time will become exponential in k as well. Like you're kind of solving an optimization problem which is like exponential in k as well. So this algorithm introduces a per term Markov chain over the state space A power k times 0, 1, 0, 1 power m, and it has a positive stationary distribution for pi epsilon. And again, we are interested in the stochastically stable states. That is the states where pi epsilon is your stationary probability is positive as epsilon goes to 0. And with using the same techniques, the set of states that maximize the sum utility is the one that optimizes this optimization problem, where array bar is sum over p of a times fm of a, but p of a here is restricted to 0, 1 by k, 2 by k, and so on. And yeah, for large enough, for small k, for a small epsilon and large k, the stationary distribution will be close to this optimal point of this, but then the mixing time will become very large. Yeah, so we proposed two distributed resource allocation strategies, and we ensured this ensured that fairness is achieved. And these are the publications.
Let's thank Ram. Stop. Questions?
Alex.
I'll talk to you later. I give you a bit of space to the other.
Reference.
No, those are my papers. Yeah.
So, as the parameters of your Markov chain goes down to zero, there is a complete characterization of the rate at which the eigenvalues go down to zero. That's what is giving you the mixing time. The mixing time can be related to the eigenvalue. So, if you can go back to the time that you need. There is a complete characterization which is due to either Friedlin or Wenzel. So they characterize how the eigenvalues go down to zero. They also indicate how the second eigenvalue goes down to zero, the third eigenvalue goes down to zero. So there is a good characterization of that. So what you're trying to do here is set it up in such a way that you beat the inverse of the eigenvalue. The eigenvalue goes down to zero exponentially fast, and inverse of that is what you need to beat. So that's why your parameter has to be changed at a slow enough pace so that you beat that. You have to essentially let it mix sufficiently long.
So I cannot take epsilon to zero. Is that what it is?
No. You can take epsilon down to zero, but as epsilon goes down to zero, the time for which you have to wait
It's going to be
longer, right?
larger.
So where is that longer coming from?
Yeah.
Longer is coming from how mixing time.
Yeah.
Mixing time is also related to the if you look at the matrix
Yeah, it's
here,
going to be the minimum probability in some sense.
yes, correct. So the eigenvalues sort of of the generator matrix for your Markov chain. In this case, it's just the transition probability matrix minus I.
Yeah.
That characterize all the performance.
So, and this ergodic coefficient is a bound for the second largest eigenvalue modulus. And ergodic coefficient is nothing but the total variation distance between any two rows of the matrix, and you take the maximum of those.
So let me ask the question, and what I'm saying will answer that question. So can you get what is the tightest bound that you can get on the top?
It will depend on the payoffs.
On the
Payoffs, like on Ri and lambda I.
yeah, and the way it will depend is through you have to look at this matrix.
Yeah, it
And you'll have to
look
study
at
that
the trees.
matrix.
Basically, you have to write down Markov tree theorem and try to. I tried doing that, but it was pretty messy.
Any other question? Okay, let's thank Ramakrishnan again.